Good evening, everyone. We acknowledge that the lands on which Memorial University's campuses are situated are in the traditional territories of diverse Indigenous groups. And we acknowledge with respect the histories and cultures of the Beothuk, Mi'kmaq, Innu, and Inuit of this province. We encourage everyone to reflect on the lands where you are located and the Indigenous peoples for whom these lands are traditional territory. My name is Gordon Slade, and I'm a director and former chair of the registered charity Shorefast. I am delighted to welcome you all to the latest installment of the Canada Ocean Lecture Series. It is a busy week and a busy time of the year, so I appreciate you all joining us for tonight's discussion. Earlier this year, we hosted a feature with Dr. Sue Malloy, another proud Memorial graduate, and I am delighted we are together again. Initiated in 2006, the Canada Ocean Lecture Series is a joint initiative between Shorefast, Memorial University, and other partners. The aim of the series is to create awareness of Canada's vast marine environment, its importance to Canadians. To date, lectures have been held on the Atlantic and Pacific coasts and in central Canada. The lecture series originated on Fogowatin, a coastal community out in the Labrador Sea. The series is an initiative of Shorefast's new ocean ethic program to complete a higher fidelity relationship with our oceans. People who earn their living from the sea can educate other Canadians about the importance of ocean conservation. Memorial is now the home hub for our series, and we're pleased to continue our partnership with the university. Increasingly, we are seeing more research and a greater focus related to world oceans. Goal number 14 of the United Nations Sustainable Development Goals, Life Below Water, calls on us all to conserve and sustainably use oceans, seas, and marine resources for sustainable development. That is an important message for all of us. Tonight's lecture is one of more than 60 events taking place during Memorial's 4th annual Research Week celebrations. The goal of Research Week is to celebrate and raise awareness of Memorial's internationally renowned research expertise and encourage more multidisciplinary collaboration among the research community, which is what tonight is about. Before we hear from our special guests, I want to provide some brief housekeeping points. After the presentation, Dr. Neil Bowes, Memorial's Vice President Research, will join us to facilitate a short Q&A. At that point in our proceedings, you can use the Q&A function that you see on your screen to type your question. An important note here, questions are limited to 250 characters, so please keep it brief and do not break your question across 2 submissions. You should keep the question addressed to Ask All Panelists option to ensure that everyone can see your question. This way, we can ensure Dr. Bose will be able to see it and it is not overlooked. Tonight's session is presented in partnership with Memorial's Conference and Event Services Unit, and we thank them for their support. We are recording tonight's session, and it will be added to Memorial's YouTube channel in the near future. It is now my pleasure to welcome this evening's special guest. Dr. David Murrin is the Director General of the National Research Council's Ocean, Coastal, and River Engineering Research Center. Previously, Dr. Murrin served as a Director of Research and Development at the NRC's Ottawa Facilities. where he was responsible for the leadership of research scientists, engineers, and technologists who carry out R&D in the areas of naval architecture, ocean engineering, coastal engineering, water resources management, and marine safety. Before joining the NRC, Dr. Murrin was Operations Director Canada for Wood Group Kenny, located in St. John's. He was responsible for strategic growth planning, negotiating agreements with clients, and understanding the offshore market and its potential for growth. In 2011, Dr. Murrin was appointed Executive Director for the Center for Arctic Resources Development, where he was responsible for interfacing with the center's Industry Advisory Committee and engaging the local community while developing and executing strategic research plan. Dr. Murrin holds undergraduate, master's, and doctoral degrees in ocean and naval architectural engineering at Memorial, where he has also worked as a visiting assistant professor. In 2012, Dr. Murrin was presented the Early Accomplishment Award from Professional Engineers and Geoscientists of Newfoundland and Labrador. I'm delighted Dr. Murrin is here tonight to present his lecture entitled Mobilizing Research and Knowledge for Changing Ocean Environments. Dr. Murrin, over to you.
All right, well, thank you very much, Dr. Slade. I'm just going to try to share my screen now, so hopefully everyone can see it. Unless I hear otherwise, I'll assume everyone can see that. So again, hello everybody. I'm delighted to be here to speak a little bit about some of the things that the NRC is doing in ocean research. And I think I have the floor for close to an hour. And I hope that at the end of the lecture, you know a little bit more about the work that we're doing across the country and how we can collaborate together on future projects. So I've broken the presentation into kind of bite-sized pieces, starting with a very quick overview of some ocean science and engineering issues, and then progressively drilling down into some project examples that might be of interest, followed by some opportunities for collaboration. I think I'll start, though, by briefly getting us on the same page on some high-level issues and priorities around ocean science and engineering. There are obviously many pieces of this, and rather than try to capture them all, I'll be concentrating a lot of my discussion around the engineering aspects of ocean and coastal research. And I'll start with some government priorities, at least that's in our wheelhouse. So from a high level, it probably makes sense to start with the biggest challenge of our time, which is climate change. Warming in Canada is double the magnitude of global warming. And with Canada having the world's longest coastline and a significant portion of our national territory above the Arctic Circle, the effects of climate change will be felt drastically by our coastal and northern communities. And as we've seen in recent days, these communities and critical infrastructure are vulnerable to risks associated with changing climate and extreme weather. And these risks are expected to increase over the coming decades due to urbanization, rising sea levels, declining sea ice cover, and shifting weather patterns associated with climate change. And the blue economy has been receiving a lot of attention over the past few years with things like the UN Decade of Ocean Science, basically looking to generate scientific knowledge and inform policies for a well-functioning ocean. There was also the Government of Canada's 2020 speech from the throne, which shows a growing interest in protecting the health of the ocean through better control of pollution sources, while at the same time benefiting from our fisheries and clean energy and transportation. The Ocean Supercluster was launched in 2018, and that focuses really on commercialization of ocean technology. And at the same time, the NRC developed plans and programs supporting the advancement of our ocean research. Another major priority of significance, I guess, for Canada and those working in ocean science and engineering is the National Shipbuilding Strategy. This is a long-term project to renew Canada's federal fleet of combat and non-combat vessels, But with overall spending expected to be around, at least on the order of $70 billion between 2012 and 2045, it's also going to provide a lot of economic benefits to Canadians and help rebuild aspects of our shipbuilding industry. So this is the sort of context in which I work, and I'll spend the next little while going over what NRC is doing and maybe how we can collaborate on some of these challenges. But first, I'd like to spend a few minutes introducing the NRC. Many of you are likely aware of and possibly collaborating with the NRC. So I'll be fairly brief, but I'd be happy to take any questions on it later. So the NRC, we have about 4,500 to 5,000 people as it changes, with about 2,000 scientists, engineers, and technologists. A lot of buildings across the country, which many of you are probably familiar with, so about 180 of those, and about $1 billion in annual expenditures. And we also do about close to 1,600 R&D collaborations each year, and we work with about 8,000 SMEs. And we really do that in two different ways. So one is through the research side of the house, which is where I work. And so we do a lot of research with companies and universities and that sort of thing. And then the other side of the NRC is really national funding programs. So that's the Industrial Research Assistance Program, which is IRAP. Just a quick map there to show you where some, I guess to show how spread we are across the country. So IRAP offices and NRC research facilities across the country. And now IRAP, I got a quick slide on IRAP. It's been around for about 70 years. It works closely with SMEs to help them innovate. And they invest close to $300 million annually for about 8,000 clients. And we also do a lot of assessments for other government departments and that sort of thing. And they support various youth employment programs. So in terms of the NRC, we've been around for over a century. Kind of started as a wartime effort in 1916. And so worked a lot in that time on concrete, advancing a lot of concrete for harsh weather and that sort of thing. And then again, for the war effort in the 40s, working a lot on radar, atomic energy, that sort of thing. And then coming out of the war, concentrating really on building Canada back. We pioneered a lot of research on the pacemaker, the electric wheelchair, and the first astronauts, the first Canadian astronauts, spun out of NRC. So they were all NRC researchers. And then into the 90s, working a lot more on health, and then into simulated brain surgery and that sort of thing. Also working on biofuel for test flights. And now in the 2020s, we've developed a pandemic response challenge program. So the idea there is to bring together the best Canadian and international researchers, really to fast track research and development aimed at COVID-19 gaps and challenges identified by Canada's health experts. And we've also completed construction of a new biomanufacturing facility to develop capacity to produce vaccines domestically and support global vaccine access. And now I'll touch on some of the areas we're looking at NRC around the ocean. So we've basically focused a number of activities aligned with helping grow Canada's blue economy. And we support science and technology development, really that balances, or at least places a balance on ocean health and economic growth. And as you can see from the slide, there are four main themes of our research. The first is coastal resilience, and it's often forgotten when we discuss the blue economy. We tend to focus on land or sea, but with changing climate and rising sea levels, storms and flooding and erosion, the interface between land and sea has to be addressed. And fishing and aquaculture and shipping, marine renewables, they all depend on a resilient coast, and coastal communities depend on it for their livelihood. So the second area there is intelligent marine assets, and that's really focusing on kind of the human-made elements in the water. And the objective there is to reduce the environmental impact of these human elements. So while we tend to focus most of our attention on ships and shipping, we also have some expertise in scalable renewable technologies, from energy mapping to testing moorings and that sort of thing. And aquaculture pens and offshore farms are a growth area for us as well. And we're also very active in developing Canadian technological solutions to enable maritime autonomous surface ships, MASS. And we're focusing on decision support tools, navigation in ice and harsh environments, and efficient and resilient supply chains. Pollution remediation is an early TRL technology theme for us, where we're trying to understand, for example, the behavior and fate of microplastics. And finally, bioassets, that's looking at the living elements in the water, most notably, I guess, microbes and algae. Microalgae can react more quickly to their environment than human-made sensors in a lot of cases. So this research is really looking at how to create algae as a sensor. So the bioasset side of things is not my focus. So what I'd like to do is profile the engineering work that we're doing that falls under my research center. So really what we do is we study the impact of water, how we can protect ourselves against it, and how we can use it to our advantage. If you think of flooding and erosion and waves, ships, ice in the Arctic, that sort of thing. And the work we do for Canada will be increasingly more important in the coming years as the effects of climate change are drastic and far-reaching, particularly on our oceans, coasts, and rivers. So the work of my research center can be separated into two main challenges. One is adapting infrastructure against the effects of climate change. Secondly, how are we going to influence the next generation of marine transportation and shipping? And as we move into an increasingly digital world, we're advancing digital models as well, our AI capabilities, and finding out how to best marry those with our world-class physical infrastructure. So just quickly now, with increased inland flood risk, coastal flooding, storm surges, erosion, our coastlines are facing a lot of challenges that we have to manage and mitigate. So in addition to that, we're also concerned with strengthening and future-proofing coastal port infrastructure. Additionally, 90% of the world's goods are still transported by ship, and marine trade value in Canada is worth more than $200 billion annually. And the Canadian Arctic and northern communities are supplied by ships. And the St. Lawrence Great Lakes seaway system is vital to Canada's economy. And also with marine transportation, accounting for up to 4% of all greenhouse gas emissions, there are important issues around the efficiency and environmental impacts of shipping. And there's also an opportunity to adopt new technologies. And we're always concerned with safety. So there are important problems to address in the ice and the Arctic in terms of navigation. And then we have to look at the future of our ports. Can we improve traffic forecasts and scheduling, port design? So there's a lot of problems that we can address. And finally, it's worth noting that we are very much involved with the National Shipbuilding Strategy. And we're working with our governments, government partners and shipyards and SMEs. And we do this using our expertise in ocean-enabled architectural engineering, and also our tremendous physical and numerical facilities, and our experience in field trials, collaborations with academia, private and public partners on very large projects. So now that we've looked at some of the focus areas for our research, I wanted to spend a few minutes on our particular capabilities and facilities. So firstly, we've been studying ice and harsh environments for a long time, and we enjoy an international reputation for leadership. We have one of the world's largest concentrations of experts in ice and harsh environments. And our proximity to universities is really a catalyst and I guess an amplifier for research excellence. And we have an ability to contribute to and work on problems at all physical scales. So full scale, field work, model scale, and lab work. and the numerical and AI work. And we're also engaged in numerous international committees and national committees and panels and working groups, participating in 26 international bodies and 65 Canadian bodies. So what I have here now is a quick video of the facilities in our research center, just to give you an idea of kind of the scale and an appreciation of how impressive they are. If I have to speak up or speed up, I should say, at a couple of points, it's because the video goes on and I want to try to keep up with it. So I'm narrating it as I go. So forgive me if I speak fast or slow down in some spots. But our ice tank facilities, they've been used to study dozens of challenges, including navigation in Arctic conditions and model testing of ice structure interactions for oil and gas platforms, and now river ice problems. So at 90 meters long, our ice tank in St. John's is one of the largest in the world. And we also have a 21-meter tank in Ottawa. So our labs are also equipped with design and fabrication capabilities. And this includes a large milling machine for fabricating our models. And following this stage, they're covered with fiberglass and instrumented. And I'll quickly walk you through the ice making process. So this tank isn't filled with water. It's a patented NRC solution to allow us to replicate sea ice and to control its thickness, its strength, and its breaking qualities. So the room is kept at -20 degrees, and we seed the air with a mist. We grow ice with columnar crystal structures, just like in nature. And then we have a system that injects microscopic air bubbles into the ice to control its density. So then when the ice is ready, we open up the door, and the instrumented model is ready to go. In this example, you see a model attached to the towing carriage. And this model is actually a polar icebreaker. And we're looking at the ice-breaking characteristics of the hull, its powering requirements, resistance. Propeller ice interactions are also very important, so we're looking at the maneuvering and ice milling of the props. And another example here is a fully instrumented free-running model. So it's not attached to the carriage, and this was for emergency ice management. The model is equipped with a working water cannon. And we do all sorts of other tests as well. This one coming up was looking at the deluge system for lifeboats in Arctic conditions. And as with everything we do, we develop numerical codes to simulate the experiments. And we calibrate these models and validate them with full scale and model scale measurements. And those three elements are a real advantage for us. So you'll see now a video of us doing full scale trials in ice for the Canadian Coast Guard. This is very important work for both of us. It's something we do year over year. NRC has widely validated expertise in recreating the material properties of sea ice at model scale, which is really crucial to the evaluation of vessel and structure performance in ice conditions. And we also do human factors work in Arctic conditions using thermal mannequins. So we also have an offshore engineering basin, and that's one of the most advanced indoor model ocean facilities in the world. And it's been an integral tool for the design and testing of every offshore oil and gas platform in Canada. The basin has been used to assess the performance, the efficiency, and also the safety of models at significantly large scale to obtain true-to-life results. Again, you see a numerical simulation, which we sometimes use to help refine our designs before testing physical models. So now our towing tank is also used to simulate marine conditions and evaluate performance of a range of marine systems. It's 200 meters in length, and it's capable of testing ship models up to 10 meters long. We also do about $1 million work for D&D every year, so the tank is deep enough to test submarine models, and it's equipped with a tow carriage fast enough to test model warships. And this carriage is precision controlled, basically a mobile laboratory that follows the models at a speed of 10 meters, up to 10 meters per second. Another good example here of us doing full-scale work and comparing it to model tests. Here we were looking at diesel engine replacements and some rescue operations, again for the Coast Guard, using a rigid inflatable boat. We also do work for the Canadian Olympic rowing team as part of the Own the Podium campaign. And working with us gives them a competitive advantage. They get to access our facilities and also the knowledge and experience of our scientists, our engineers and technologists. So now we move to our Ottawa facilities. We have the NRC's multi-directional wave basin. That's used to assess the performance of marine structures using wave machines, and produce a range of wave conditions. The facility can be rapidly drained and filled to recreate bathymetric conditions. Local wind fields can be simulated using computer-controlled fans. And the large area basin we have there is ideal for conducting large three-dimensional hydrodynamic studies. The wide range of wave conditions can be generated using powerful 72-segment wave machines, water depths up to a meter deep. And we have large pumps and thrusters and weirs. And they're all available to produce tidal flows and simulate discharges from inlets and rivers and culverts. We also have a coastal wave basin there. That's basically a narrow 3D basin or a very wide 2D flume. And it's really good for conducting 2 or 3-dimensional studies of wave and current interactions with structures, shorelines. And we can generate long crested irregular waves and also bidirectional currents. And the basin is easily accessed by a heavy equipment and a 1-ton gantry crane. So this was a very quick overview of our facilities. And while it's not the same as being here, I wanted to show it just to give you a sense of the sorts of things we do and how impressive our facilities are. And in addition to the full scale and model scale work we do, we try to replicate all of our work digitally. So we use various techniques from traditional, I guess, numerical physics-based simulations to AI, artificial intelligence. And we use all these different approaches to validate and calibrate one another. So I've given a lot of the background and the motivation for our work. And I wanted to spend some time now highlighting some really interesting research projects that I hope are interesting to you as well. The first one here is just a brief example focused on research to support the greening of marine operations, focusing really on the reduction of fuel consumption and its related air emissions. It's directly related to a number of Canadian and global initiatives that aim at, that are really aiming at mitigating climate change. So in the next 2 slides, I'll discuss 2 specific projects that are ongoing at NRC. The first is the Canadian Armed Forces is, as you can imagine, a big consumer of power and energy, and it's been tasked with finding more sustainable ways of accessing energy at a reasonable cost. So Defence Research Development Canada, DRDC, started developing these replicates of the Halifax class frigates, basically to produce energy models to help them analyze power demands and fuel savings and GHG reductions under various conditions. So we're working with them to validate an anticipated 10% reduction in GHGs against a baseline of the fleet's emissions. So kind of as an example, you have a fuel consumption model that incorporates parameters from multiple ship systems. And then you can evaluate the fuel savings resulting from, say, swapping out a generator, an older generator with a modern, greener unit. And on the West Coast, BC Ferries are interested in many initiatives to increase vessel efficiency and consume less fuel and protect the environment. So they are one of the world's largest ferry operators. They move about 60,000 people a day, 35 ferries. And they wanted really to assess the effectiveness of a really smooth hull coating. It was aimed at reducing hull friction. So they collected about 10 months worth of data before and after applying the test coating. And we worked with them to measure the variation in power demand before and after the coating was applied. And the data accumulated minute by minute really requires advanced analytics and machine learning techniques and AI. So we retained a graduate student actually from Simon Fraser, specializing in machine learning, really to delve deeper into the data and manage the complex analytics. Really, one group can't have all the capacity that you need for these things. So being able to draw on various sources of talent and facilities for knowledge and expertise is really important. And this slide just lists a number of other projects that we're currently working on in the area. And through the research, we're collaborating with a number of key Canadian vessel owners within the federal government, but also the private sector to help them solve challenges relating to the greening of their fleets. And the common theme really is to develop these data products from operational data that's measured aboard the vessels. And that'll help support the next generation of marine vehicles that are greener and operate more efficiently. So now another really interesting example is on coastal flood mitigation. So one of the first priorities for effective flood risk management is really to develop a strong understanding of risk. And this has been the focus of our Coastal Flood Mitigation Canada project, which really is a collaborative research project that we co-developed with NRCan 3 years ago to develop regional hazard data sets and best practices and guidance for assessing coastal flood risk. And this really involved drawing on lessons learned from case studies conducted in partnership with 3 communities, one on each of Canada's marine coasts. And as you can see in the list of collaborators here, this is a good example of a project involving a number of collaborators from coast to coast, from federal, provincial governments, First Nation communities, private sector, and universities. And the project is in its final year, but we're already seeing the fruits of the work, really, which includes new regional storm, surge, and tsunami data sets, an improved understanding of risk within the communities we partnered with, and a new draft national guideline for coastal flood hazard assessment, which will be integrated into the federal floodplain mapping guidelines series. And I will mention just one interesting research finding that came out of it. And that was numerical modeling studies demonstrated the role of sea ice in attenuating storm surges in the Western Arctic and the Gulf of St. Lawrence. So, that could have implications in a future climate as well. So moving on from the first step, really was understanding the risk. Now we switch to research enabling improved coastal flood and erosion risk management. And here we've been conducting research to address knowledge gaps surrounding the coastal resilience benefits of nature-based solutions. So nature-based solutions are quite widely adopted internationally, but they remain kind of underutilized in Canada. And so we're now leading a new multi-year project to address some of these gaps and develop design guidance around nature-based solutions. So we developed a living laboratory style approach where we have 3 parallel lines of research, so experimental, numerical, field-based, ongoing at multiple pilot sites in Canada. And this started with about 3 sites, but with growing interest and the help of some collaborative grants, we're now up to about 6. And again, here we're working with community partners to ensure that local and traditional knowledge is embedded in the work and that the resulting design guidance reflects the needs of the users. And our work on nature-based solutions over many years has positioned us well for collaboration and to develop practical tools and guidance. So last month, the U.S. Army Corps of Engineers launched peer-reviewed international guidelines for nature-based solutions, which was the culmination of several years of collaboration between more than 77 agencies around the world. And we represented Canada in the working group, and we co-led the development of one of the chapters. And closer to home, we completed a review on behalf of CSA, which really steer their efforts towards standard development to enable nature-based solutions in coastal and riverine environments. So I also have another interesting project we executed that's called the Springbank Offshore Storage Reservoir. And in this case, the Elbow River in Calgary is susceptible to flooding, and often with catastrophic results, as you can see in the slide. So the Springbank Offshore Storage Reservoir, it was conceived really to divert part of the flows of the Elbow River to an off-stream storage reservoir that gets gradually released after the peak of the event has passed. And as you can see in the lower left, where in normal conditions the Elbow River flows really through this service sluiceway. And in flood events, the diversion inlet opens and diverts the flow to the reservoir. But there were several design issues here presented, and in particular, woody debris interaction. So as you can see in the lower right, the floodplain has a lot of woody debris that gets transported during flood events. And these are a fair size. These are up to 1 meter in diameter and 16 meters in length. So they can cause issues for the proper operation of any hydraulic structures. So we constructed a large 1 to 16 scale physical model in our facilities. The model was really too big to get a good shot of it, but you can see the researcher in the photo in the top left. So a large scale model was used using real debris as well. So we modeled the debris, and that increased the realism of the physical model. And over the course of 4 months and several hundred tests, we got a lot of really interesting data. And the model gave some insight into the behavior of sediments and debris. And the top right photo shows just how quickly debris jams formed in the original design. So the physical model played really a key role in the risk analysis and the front-end engineering design of the structures, and really helped validate the layout of the structure and optimize the design. Also of note, one of the research papers that we wrote for this received the award for Canadian Dam Association Published Paper of the Year. So this is a brand new facility here, a frazzle ice facility. And the background for this is, so power plants in France, they really experienced frazzle ice events at locations throughout the country over the past several years. And this kind of poses a risk to those installations as you get an accretion of ice crystals on cooling water intakes. They can really threaten to block cooling water flow, potentially cause cooling systems to fail. So to better understand and hopefully eliminate these issues, we've been collaborating on the design of the intakes and understanding frazzle better. And in parallel, our partners are also attempting to numerically model the frazzle accretion process. But they can't really be validated that accurately because there's no available data to do so. So we've proposed a way to produce frazzle ice in the St. John's ice tank and collect the required data to validate and improve the understanding of the physics and the governing processes and refine the code. So what we did was we modified our St. John's ice tank to generate frazzle under controlled conditions, which temporarily makes it the longest refrigerated flume in the world. So we've commissioned the facility and our objectives for the research are already to measure the suspended frazzle and build a trash rack that can be submerged to collect frazzle ice during events and measure the amount of ice that accumulates in the trash racks. So this was a very, very big project. It's not complete yet. We're going to be doing more tests in January, but we basically we got to use our facilities for something a little bit different too, which is nice. That ice tank has traditionally been used, as you saw in the video, for ice breaking and that sort of thing. But now we're looking at new possibilities with it. And what we're hoping to do is, and now that we can recreate frazzle events, we can actually hopefully bring it to North American customers and clients and that sort of thing to help them deal with their frazzle events as well. And so now I want to just touch on our numerical modeling and forecasting. Basically, I have an overview of a subset of 4 numerical models developed at NRC, where we focus on sea ice modeling and forecasting. So to organize it, I sorted them by kind of temporal and spatial resolution. And I'll start with a new very high resolution modeling approach using smooth particle hydrodynamics, or SPH. And then we'll follow that by small scale ice dynamic models. And then the third model is our regional scale ice forecasting system. And finally, I'll present a medium term ice presence forecasting at larger scale. But I'll just go through these very quickly. So starting with the first model, there are a lot of recent improvements, obviously, in computer technology and more specifically GPUs. And they're now providing the required computer power necessary to conduct large experiments using smooth particle hydrodynamics. And really the long-term objective here is to develop numerical capabilities for accurately modeling complex materials, so ice, along with hydroelastic structures and predictions of small scale and large scale wave structure interactions. And it shows a lot of promise. Really good at highly separated and complex flows, and wave breaking and wave structure interactions. And usually when you study these things, the complex materials such as ice and hydroelasticity are often handled by combining multiple methods. But this allows us to do it all at once, which is really encouraging. So we have a new collaboration with Environment and Climate Change Canada and McGill University for developing these SPH-based ice dynamics models for large and small scale applications. And that'll include the validation of the model using the ice tank in St. John's and our offshore basin data. We also have developed over the number of years a high resolution ice dynamics model at scale relevant for ice structure interaction. And we validated that against field data used for ice management and those sorts of applications. And as you can see in the animation, simulation of river ice dynamics and modeling the interaction between river banks and bridge piers and that sort of thing. We've also developed a pressured ice forecasting system, and we're currently working on modeling an ice deterioration aspect to it that's really caused by wave action. And that's of special interest to offshore operators. And this system is currently being used by a number of offshore operators and Canadian government agencies. So finally, looking at a longer term time horizon for ice presence, basically for planning, strategic and tactical planning, that sort of thing. We wanted to develop something that looked out further than the 30-day forecast typical of national weather agencies. Because this information is important for the shipping industry to allow them to plan for safe and efficient summer sea lift operations for the Canadian northern communities and to deliver their yearly resupply of fuel and goods. So we developed a model for forecasting up to 90 days in advance. So that's quite an improvement over the 30. And it's forecasting the probability of sea ice presence in the Canadian Arctic using deep learning algorithms. So the animation on the right is a sample product from our AI model and forecasting breakup in June in Hudson Bay. And the model uses as input weather conditions for the last 3 days and optionally the atmospheric forecast for the next 30 days. And it predicts the probability maps for the next 90 days. So one real added advantage to it is the efficiency that we can generate these models in. Once the model is trained, it requires about 4 seconds to infer a forecast just on a regular workstation. And that's compared with several hours on HPC infrastructure using traditional methods. So established from this collaboration with the University of Waterloo, we recently initiated a new collaboration with Environment and Climate Change Canada and FedNav and McGill to apply a similar approach at a higher resolution on the St. Lawrence Seaway. And that focuses really on the Port of Montreal. And that's going to look at climate reanalysis, but also Environment, Climate Change Canada, ECCC. They have in situ sensors as well. So we're looking at incorporating those sensors to give us even more accurate results. We've also been studying marine safety for over 20 years. And Canadians, as we all know, are exposed to some of the harshest environments on Earth. So, we have the Arctic and the Atlantic Ocean. And really to help both operate effectively and save lives, a combination of equipment and regulations are needed. And in our experience with marine safety, equipment will oftentimes only meet regulations and rarely exceed it. And so you have a knowledge gap then when equipment is used in conditions for which it was never intended or tested. So we use our facilities and expertise to simulate these harsh environments and address knowledge gaps. So an example here, we worked with various branches of the military to assist them in testing their equipment in harsh environments, basically to establish its performance. We've tested existing uniforms and sleeping bags and submarine escape suits and immersion suits and other pieces of kit so the military can select the best equipment for their personnel. And we're also investigating the effectiveness of incorporating clothing made by indigenous crafters. We combine that with existing uniforms, basically to combine traditional knowledge with existing equipment. We also do a lot with the International Maritime Organization. So that's a specialized agency of the United Nations. And it's responsible for measures to improve safety and security of international shipping and prevent pollution from ships. So we work with Transport Canada on IMO correspondence groups, basically to help draft new regulations and international guidelines that will impact how Canadians operate in harsh environments. And this may be my final one. We also help mariners make better navigational decisions that will reduce risk and save fuel. So we've developed in our ice tank, basically we've got a method to help capture ice through cameras and machine vision. And we can identify many ways to plan a path in that ice. And that includes ice dynamics and channel widths, etc. So in our case, we have 20 cameras throughout the lab, and we've developed a real-time calibrated system using image processing techniques to manipulate the image and ultimately define the edge of the pieces and provide kind of a binary, ice or no ice for us. And you'll see here a demonstration of the real-time system. On the left, you see a model vessel in the basin. And then you see a PC showing our test bed software with interpreted ice pieces. And then on the right, you see a model vessel advancing through an ice field. And you'll notice one of the key complexities here is that the ice moves as the ship interacts with it. So it requires a constant updating of the desired path. There are just a few examples. Now I want to just touch on maybe the ways that we could collaborate together across the country. So at the NRC, we achieve our vision in 3 different ways. One is advancing scientific and technical knowledge. Second is supporting government policy objectives. And thirdly is supporting business innovation. So in terms of advancing science, we work with academia. And as you can see by some of the project examples, we spent a lot of time over the past 2 or 3 years developing relationships with universities and research organizations. Collaboration is really the key to advancing knowledge. And so we're involved in a number of consortia, and we've signed MOUs with research organizations and institutes in Canada and internationally. And we've also dramatically increased our number of students. In my research center alone, we've gone from close to 0 3 to 4 years ago, and we now have 35 to 40 students per year. And they have a big impact on our work, and it's great to have their energy and their ideas supporting our research. And we've also increased our number of collaborative peer-reviewed publications. And all this increases our visibility and yours, and credibility and reputation on the world stage. And before the pandemic, we also offered our facilities and technicians for some undergraduate curriculum, which has been really fun. The NRC also is going to invest a little $10.5 million in grants and contributions over the next 6 or 7 years for collaborative research projects aimed at, and this is around ocean in particular, aimed at enabling SMEs and developing solutions and supporting students and academics. And these are represented across the country. So they're called grants and contributions. They're basically given through a collaborative project with NRC that'll support either students, an academic institution, an SME transition technology to market, or it could just be complementary research to NRC's own research. And so just as some examples, we have 10 student ships have been launched with OFI, so that's DAL, MON, UPEI, and 5 projects for MASS through an open call. So MASS, again, is Maritime Autonomous Surface Ships. And through that open call, we have 5 projects in Newfoundland, Nova Scotia, Ontario, and Quebec. And we also have about $1 million in collaborations with SMEs. So about 2 years ago, the NRC also launched an initiative to kind of co-locate researchers from universities and NRC to work on common problems. So we set up a number of these collaboration centers. You can see the list of them there. And the one I was responsible for here is, well, one of the relationships that I've really been working on is the one we have with Memorial University of Newfoundland, Labrador. Our building in St. John sits on MUN's campus. We have a long history of working together. So in June 2019, we opened the Carlick Collaboration Space, which is really focused on ocean engineering and bringing researchers together again. Ocean science and engineering, I should say. And the name Carlick, for those of you that aren't aware, it was a sailing ship captained by Bob Bartlett, Newfoundland's Bob Bartlett, for the Arctic. And 1 month into the journey, it became trapped in ice and sank. And so today, really, the Carlick is a symbol and a reminder of the challenges associated with operating in harsh environments, and also the innovative solutions needed by Canada's top researchers. So the space was originally developed back when we were encouraging collisions between people, and was a physical space where students would have their offices and access to their projects and facilities and that sort of thing. But we've had over 25 MUN students with their supervisors involved in Carlick projects over the last 2 years. And that includes graduate students, postdocs, undergraduate students. We're still working out how to get them back into the building now, but the collaborations have continued nonetheless. And a really good example to demonstrate our renewed collaborative relationship with the university is this harsh environment research facility. So this was Memorial's was awarded a CFI grant with funding from other parties as well. CFI, MUN, Husky. But we're in discussions with them now on an agreement to facilitate collaboration between our researchers and MUN's researchers using this harsh environment research facility. We do work with government. I'll just touch on that very quickly because I think I've touched on it, probably know. We support a number of government departments. So we have strong links with the Coast Guard, Transport Canada, DND, DRDC, Royal Canadian Navy, Environment and Climate Change Canada, NRCan, provinces and territories. So we're really an important link in supporting various government mandates, including those device breakers. And finally, the third area of focus here is on supporting business innovation. So about 50% of our projects are for Canadian SMEs. We directly support the Supercluster on a lot of these projects. We have MOUs with SMEs, we have a strong international presence and collaborations. And we work really closely with industry to advance their designs, and most importantly, to ensure that they're safe. And we do this in a variety of ways, sometimes through collaborative activities, and sometimes through pure fee-for-service research. And this is just a cross-section here of Canadian companies that we've been working with. Not exhaustive by any stretch, but it does cover the entire range from very small, including startups, to very large companies. And thematically, the companies span a wide range, including engineering consulting, technology innovation, naval architecture and shipping, energy. It also includes industry associations and key players in the innovation space. And some work is also done through, like I said, the Ocean Supercluster. So this slide just shows various ways that SMEs and industry can work with NRC. So we have, again, work through the Supercluster. We also have a fee reduction program. So for SMEs, you're eligible for a 40% reduction in labor. We also have a certificate program at IRAP, which gives 50% of the costs up to a maximum of $50K on the contract to carry out work at NRC. And these programs are very flexible and they can be stacked differently. So finally, I'd like to thank you all for your time and your patience. I know I crammed a lot in there, but I hope you see how we're involved all across the country. And like I said earlier, collaboration is the key, and we're always looking for ways to collaborate on research of mutual interest. If you see any alignment with your work, I'd love to hear from you. Thank you.
Thank you, Dave. That was really great. And great insight too, and coverage. As you know, ocean-related research is a top priority at Memorial as well, and hence the CARLOC collaboration. And over 40% of research at the university is ocean-related.
Yeah.
And in our new strategic plan, the key area of research identified is ocean-related research. And the idea is to sort of focus on that, become a trailblazer in the world, more so than even in the past. So we've really valued our long-standing collaboration with NRC generally, but also the OCALAB and its various incarnations in the past too, IMD, IoT, I've lost track of them all.
I just say NRC now.
NRC, yes. And it's a really good setup to be linked so closely too with your Ottawa facility. So a reminder to those joining us virtually that if you've got a question for Dave, you can now type that into the Q&A function on the right-hand side that you see on your screen. Please keep your typing to less than 250 characters so that I don't have to try and piece together more than one comment. And you should keep the question addressed to the Ask All Panelists option so that I can see it and it won't get overlooked. So let's take some questions. I don't see anything in the chat line, so I'm going to fire away myself. Early on, Dave, you talked about autonomous surface ships and microplastics work that NRC is doing. Tell us about what sort of things are going on at NRC in these two areas.
Sure. So yeah, the maritime autonomous surface ships, that's a big problem, and I don't mean a problem in a bad way. I mean it's a lot of parts to solve, and so our lab, we obviously won't be looking at all of it, but some of the things that we're looking at are defining paths, identifying better ways for forecasting of ice and that sort of thing, and supplying that information to ships. And some of the digital work that you're seeing in the lab that was navigating through paths in ice and that sort of thing is all very informative. But there's also some work going on at NRC, because one of the other research centers across NRC, we cover a lot of different areas, is automotive and surface transportation. So as you can imagine, when something does arrive in a port, if it's a shipping container or something like that, it's got to come off the ship and go on a truck. And is there ways to automate those things and make them more efficient? So that's something that we're looking at. And in terms of the algae side of things, so we have a lab it's in Halifax, it's in Ketch Harbor, and it's in Charlottetown. And they focus really on seaweed and that sort of thing, and they're really world experts in seaweed. And they're trying to make a lot of products from seaweed, but also there's a real effort to work with other research centers, so kind of interdisciplinary work, where we can figure out, okay, how does some of the problems that we're working at with maybe detection of oil spills and that sort of thing, can we use some of these algae as sensors and work together where we bring our engineering knowledge together on something and combine it with kind of the science knowledge that they would bring. So this is really interesting, and this is part of our focus on bioremediation and that sort of thing. So it's trying to figure out the best way to work together. And I think that some of the work that we're hoping to do with aquaculture and that sort of thing, which we haven't even touched on, it will involve some interdisciplinary work where we have a lot of our experience with offshore platforms and that sort of thing, but not a lot of experience in this lab dealing with fish farming. But we have another lab that does that, so figuring out ways for us to work together on these things as well. So that's kind of the areas that we're working on.
Thanks, Dave.
Dr. Slade, I'll get you unmuted there, Gordon.
You're on mute, Gordon.
I sent you a request there. It should pop up on your. Try not to cross it out.
Okay.
There you go.
Yeah, I had a question about your ice modeling.
Yep.
Pretty interesting because last year there was no ice on the northeast coast of Newfoundland, none. And of course, there's people would say with the melting of the glaciers in Greenland, you would think there'd be more ice coming down rather than less ice coming down. So people are asking the question, what will happen in 2022? Will we be seeing any ice again in 2022? So your modeling work that you showed us here, is that now running? Can you do some forecasting on what you can expect in the next 90 days or?
So we do the 90-day forecast fairly well. As you can imagine, the whole state of the climate has thrown a real wrench into climate models and ice forecasting models and that sort of thing. And so that's the approach we took was using something fairly recent. So we do a lot of satellite machine learning through satellite and that sort of thing. So it gathers a lot of that information. But then if we can get a forecast or at least some data close to a number of days beforehand to feed into it, we've been very accurate with the 90-day forecast. Going beyond that is still a stretch, though.
Thank you.
So, Dave, you mentioned the different natural environments and so on, and you talked about erosion risk and coastal flooding and nature-based solutions, and you also talked about local and traditional knowledge. Could you give us an idea of what sort of things have cropped up in the understanding of use of traditional knowledge to present flooding and erosion?
Yeah, so that it's still underway. So I don't have a lot of details on it yet, but the key part was working with those communities. So we make sure we have Indigenous communities involved. And so as we're planning our experiments and asking them, what they have found, it's been really useful because the shorelines themselves in some of these communities they're really eroding really quickly, and even their observations, I think they're noticing that it's accelerating. It's not something that people they've had a house on a coastline almost completely eroded away, and they've had to relocate and that sort of thing. So the actual results from the Indigenous knowledge hasn't all been incorporated yet. It's an ongoing research project, but I can't really comment on that yet. But the big thing this year was finding, even for our lab, finding suitable plants. So we grow real plants in our lab now, and we're testing those in our flumes and seeing how they work as nature-based solutions and that sort of thing. It's really a technology that's or an idea that's starting to take off in Canada, and in a couple of the blue economy documents and that sort of thing, they've stressed nature-based solutions and resiliency and that sort of thing. So I think it'll just get busier and busier in the coming years. But yeah, it's probably too early to comment on those results yet.
Well, the modelling showed the attenuation of the waves with various weeds growing, right?
Yeah.
And later on, you talked about indigenous input to cold weather gear. What sort of insights were shown up there?
So that one's really interesting. So we're working with a number of craft councils across the north, and they're doing various types of equipment. So they might be doing mitts, but they also do they various garments and that sort of thing. And we're comparing it with a lot of the actual military equipment that we're using right now, and finding them, I shouldn't say surprisingly, but very, very impressive. They're outperforming a lot of the equipment, and in harsh conditions. Like they're not being biased in any way. So the trick now with that project is going to be looking at kind of the quality control, because if we go to 20 different crafters, are they all going to be built the same and that sort of thing? But that first stage of that project finished probably a couple of months ago. But the biggest thing that came out of it was really how impressive some of these different pieces of equipment are. And so getting then the military involved and showing them the comparisons between these various garments is it's a new way of looking at it, but probably shouldn't surprise a lot of people. They've been perfecting it for thousands and thousands of years.
Well, exactly. There wouldn't be anyone left living in those regions if they hadn't have worked.
Yeah, exactly.
Now, I don't see any questions, and I guess everyone's dying to get away and have a glass of beer or glass of wine or something. And no doubt you and I could carry on our conversation in similar circumstances. So I'm going to say that winds up the lecture, and I'd like to thank everyone for joining us online for this year's Canada Ocean Lecture Series. We're very proud at Memorial for the ongoing collaboration with Shorefast, and now that we've become a home hub for the series. And I'd like to offer my thanks to those who helped organise tonight's session, including all of those behind the scenes, and special thanks to Dr. Gordon Slade and Shorefast and John Duff and the entire team from the Conference and Event Services with Memorial Signal Hill Campus. And obviously, and finally, big thanks to you, Dave, for sharing NRC's perspectives with us. And I hope everyone has